So this video is the 7th lesson for Chapter 7. It's the lesson that's partnered up in a nice way with Lesson 6. We're looking at Faraday's law of induction, how you can use magnetic fields to actually generate electricity. Last day we were really focusing on Lenz's law, where you can figure out which direction the current's going to flow. Today we're going to look at how much current's going to flow. Specifically, we're going to look at how much voltage you can generate with this changing flux. And then from that, you can easily use Ohm's law, which we will in this one example for today to find the current. So we're going to put all of our marbles into one basket, all our eggs in one basket, or whatever you want to call it, and put all the ideas into this one example. So there's going to be quite a few things going on in this example. It kind of it occupies the whole page in your notes there. Try to write a little bit small because there's some stuff on the bottom half of the page that I like to add at the end. But it's going to be a pretty quick lesson here today because there's just the one example. So what do we have? It says a 50-turn coil. That's in black. I know you just see a single little black rectangle, but I want you to imagine that somebody has wrapped wire around in a rectangle 50 times, and then they've taken the two ends of wire and just connected them together. So it's this continuous solenoid that's actually self-closed. It's pretty large, 3 meters on this side. Actually, it's huge, 5 meters on that side. And so overall, all of that wire in this story has just 8 ohms of resistance. Now the magnetic field, the external magnetic field that's shown in blue, it's going to change from 2.4 Teslas going into the page, that's why there are X's, to 1.8 Teslas coming out of the page, and that's why we have the dots. Now that blue magnetic field is an external magnetic field. It's caused by some person holding a magnet nearby. Okay, so please don't think that this magnetic field shown in blue here or in the after picture is caused by this black loop of wire. That's not the case. This is the applied or external magnetic field, or the first magnetic field if you want to call it that. But we're going to make a change, and it's going to go from being really strong in to fairly strong out. We're going to do it all very quickly in less than half a second. And you're asked to find the size and the direction of the current that flows in this black 50 loop rectangle of wire. Let's do direction first. So this black loop of wire does not care how much flux there is, but it just does not like change. So the fact that there's 2.4 Teslas of magnetic field going in, well, that black loop, if you want to personify it, it's like, yeah, I'm okay with that. Please don't change it though. And we're going to change it. We're going to change it from that 2.4 in, which I've just depicted with 6 X's, to 1.8 Teslas coming out. And I've just depicted that with 4 dots. So that loop of wire is going to say, whoa, I do not like that change that's happening. And during the change, it's going to make its own voltage, to make its own current, to make its own magnetic field, which I'm going to draw in green, a second magnetic field that tries to battle you. It tries to get back to this picture that had the 6 X's. So right now, 4 dots. How can I make 4 dots actually look like 6 X's? And the answer is add a whole bunch of X's. The first few that you add just neutralize this set of dots. So if I was counting dots and X's, which you don't really have to do, but if I was, I would probably draw 10 green X's. The first 4 X's cancel out the blue dots. I don't want them. And then the next 6 X's get me back to where we were. So again, the blue magnetic field is from some person holding a magnet, spinning it around, I guess. And the green magnetic field is caused by that loop of wire, those 50 loops of wire. So how would this rectangular loop of wire generate all those X's? Well, let's grab the wire, maybe right here with your right hand, and grab it in a way where as you grab the wire right here with your right hand in your mind, your fingers behave like these green X's, right? So your fingers have to go into that rectangle. So just imagine as just grabbing it like a fist, grab the wire right here and make sure your fingers point in. And what you'll find is your thumb is actually going to point to the left. So you've actually got this created or induced, as we call it, current going clockwise in this picture. I can't say this too many times. That clockwise current only lasts for 0.45 seconds. It lasts during the time you're making the change. As soon as you stop changing that magnetic field, even once you leave it at 1.8 Teslas out, then that current goes away. But during that 0.45 seconds it takes you to get there, that current will be happening. Hey, we've got half the battle done. We have found the direction for the induced current. Now we have to go find size. And as I cautioned you before, this example has a couple of little curveballs in it. The main one is that we are switching the direction of the magnetic field around from fairly strong in to fairly strong out. So at the beginning, I'm going to check out how many Webers of flux there is. It looks like it's flowing beautifully through there. 2.4 is the value for the magnetic field. 15 is the area. Okay, so you have to find the area. Rectangles are easy. Sometimes you have to do circles with pi r squared. But here it's 15 square meters, and that's 36 Webers. Now, I personally have just put a little plus sign on this. There's no real standard here, but I just wanted to make a little note to myself that, hey, that flux is going one direction. It's going into the page in this rectangle that's here. Okay, what about the final flux? Well, it's 1.8 Teslas of magnetic field. It's a slightly smaller magnetic field, still 15 units of area, and I get 27 Webers, but there's a catch. It's not in the same direction. Now, personally, just personal choice, I'm using some pluses and minuses just to really highlight that for myself. As long as you understand that those 36 Webers at the beginning were one way, and the 27 Webers in the end are a completely different direction, like you've done a U-turn, we're okay, right? But now I want to ask, well, how different are these two fluxes? Because we're going to have to find that speed that the flux has changed, the Webers per second. So I'm going to put some notes here in red. If you can squeeze them into your note booklet, that's great. You don't have to, but I just want to point out that these two numbers are very, very different. Plus 36 and negative 27, they're not just 9 apart. They're actually 63 apart. Or some people might say negative 63 apart. Whatever. They're just, don't say they're 9 apart, right? They're very, very different. Like, can you imagine if one day the temperature outside was plus 36 and then the very next day it was minus 27? You would definitely be telling people that it changed by more than 9, right? It went all the way through 0 out to negative 27. I personally like to call that a U-turn, and sometimes you'll see that in stories where the magnetic field doesn't just diminish from 2.4 to 1.8. It actually completely changes the other direction. So we've got a change there that's actually 63 Webers, or negative 63, okay? All right, the equation. We saw this a few days, or last lesson, the voltage generated. There was a minus sign right here, which I've actually ignored. That's actually Lenz's law. And then there's the number of loops, capital N. Okay, so this was the equation near the beginning of the day in last lesson. And then right here was this fraction, change in flux, all over change in time. And so you can see as I calculate the change in flux here, it will not be the number 9. It's actually going to be a number that's 63 big. There is a negative sign in the equation that should go right there, but you've already dealt with it. That's how you find this direction for that induced current. We spent a minute at the beginning of this example and figured out that the direction for the current's clockwise. That negative sign for us in high school is just a reminder about how that works. It's a reminder of last day's lesson, so you don't need to put it into your math. So I'm actually going to ignore it. Okay, these numbers, again, when you subtract, you actually get 63. The mathematicians who say, oh, final minus initial, would actually say negative 63. Sure, as long as you get a number that's 63 big. Just don't say 9, right? I'm actually going to ignore this minus sign. And this division, the 63 Webers, divided by the 0.45 seconds, that's that fraction, that change in flux over change in time. So this value divided by this value is calculating the Webers per second. Okay, if we multiply the Webers per second by the number of loops, every single loop generates some voltage. So I actually get this massive voltage of 7,000 volts. I should tell you that that only happens for 0.45 seconds. As soon as those 0.45 seconds are done, the 7,000 volts goes away. But during that half-second time, you can figure out the current by just doing Ohm's law, just the voltage divided by the resistance. You would have this impressively large 875 amps, and it's going clockwise. So we've done it. We've found what they wanted. We found the size and the direction of the current. The current size, you had to use Ohm's law to get there. And the direction, we used Lenz's law in order to find that direction. Now, hopefully you've still got a little bit of room down at the bottom of your page. I just want to show you a neat little calculus technique you can use to maybe speed things up. and maybe come up with this 7,000 volts a little bit faster. So this is just for the sake of the people in class who have a little bit of calculus experience. If you are not in calculus class, don't worry about this part. Okay, it's just, again, for those that are taking calculus, this can help you out. So there is actually Faraday's law. It's what we just used to find the voltage. We had a 50 go in for the number of loops. We had that change in flux, that was 63, and the change in time, that was 0.45 seconds. The part that I've circled there in green is a derivative, right? It's that rate of change in flux, right? In university, typically you would write that d phi dt, but here we're using the big deltas, and that's fine. Now, thinking about calculus, just thinking about the product rule, right? So think of this as d phi dt, or b times a dt. Calculus people would tell you, oh, the product rule works like this. You have to do the derivative of the first factor, so there's the derivative of b in blue, multiplied by the second factor left alone, there's the a. Then you would add, leave the first factor, and multiply by the derivative of the second factor. How fast is the area changing? The reason why I wanted to point this out is most questions don't have both the b and the a changing. Typically, there's only one change. So if the magnetic field is constant, but somebody is crushing the area, like stepping on some solenoid to permanently damage it, then you would have a derivative of b that was 0. And you could actually say, oh, well then the change in flux over change in time, it's just your steady magnetic field multiplied by how fast you change the area. I gotta tell you, that's pretty uncommon. Most people don't like stepping on their solenoids and destroying the area because you can only do it once. But this one is very common. What if you keep the area constant like we did at 15 square meters? Then that derivative of area is 0. It didn't change. The only thing that's changing is the b. So a faster way that we could have come up with that 7,000 volts would have been to say, oh, well, the change in flux over change in time is really just the change in magnetic field over time multiplied by your stable area value. So we could have done this question this way. Okay, looking at that story, we could have said, oh, there's the base equation, but we know that this flux deal is b times a, and it looks like only the b is changing. So we could have asked, how fast is the b changing? And then multiplied that by the area. Now the b, it goes from 2.4 one way to 1.8 the other. It's a big change. It's actually a change of 4.2 Tesla because it does the U-turn. But maybe the numbers might have been a little bit nicer to take this 4.2 value, right, how much the magnetic field changed, divide by the time, multiply by the number of loops, and then multiply by the area. It just speeds things up a little bit, keeps the numbers a little smaller, and you would end up with, when you have that change of 4.2 Teslas in 0.45 seconds, you'd get that 7,000 volts. So it's an option when you know that the area is not changing to modify this Faraday's law of induction. Instead of writing it as n, change in phi over change in t, you could go n, change in b over change in t times the a. And it's just one option to get there a little bit faster. Most of the time you don't see that U-turn, but it does happen every once in a while. So that example actually is as hard as it can get. Most of them are actually a bit easier. And that's the math for Faraday's law of induction.